Hello everyone, let us start our third lecture. As we have discussed in our first two lectures on importance of studying corrosion, we have also given some examples, some of the catastrophe we have also mentioned, and finally as we go ahead and then we have seen that corrosion involves 4 parts and it also is directly associated with electrochemistry, and the 4 parts are 2 electrodes, which is one is cathode, one is anode. We have electrolyte where ions will be flowing, and then we have conductor where electron will be flowing, and then we have a complete circuit, and then corrosion will go on. So, corrosion is electrochemical in nature, that is what we have understood. And we have also given 2 examples, one is zinc corrosion in dilute acid, where on the zinc plate you have hydrogen bubble, and this hydrogen bubble is forming due to cathodic reaction, which is hydrogen plus ion takes 1 electron and it converts to hydrogen atom, and then finally 2 atoms join together and forms hydrogen gas, and that reaction happens on zinc surface itself. And this particular electron is coming from formation of ions of zinc, which goes into solution from the metal part, and that electron will be released into the metal, and then metal acts as a conductor, and that electron comes to the place where hydrogen evolution reaction happens. So, that way the circuit is complete, and this zinc actually finally forms zinc chloride, because already you have chloride in that particular HCl medium, and that way zinc corrosion goes on. We have also given example of iron corrosion in atmosphere, and if I go back and try to see that particular slide, if you see that iron is actually going to iron plus 2 ion, electrons are released, and these electrons are taken by cathodic reaction, which is oxygen plus 2 H2O plus 4 E equal to 4 OH minus. And here we have seen that this particular ion reacts with this H2O plus O2 and goes to FeOH whole 2. In fact, this particular reaction is anodic reaction, and this particular reaction is cathodic reaction, which happens on the iron surface itself. Now, this iron plus 2 reacts with OH minus and forms FeOH whole 2, which is same as this reaction. Finally, this reaction is parallelly taking place. This is also electrochemical, because this is anodic reaction, this is cathodic reaction. This anodic reaction happens on the iron surface, iron corrodes, and cathodic reaction also happens on the iron surface, which takes care of that electrons which are released by iron while formation of ions. This is also electrochemistry. Now, we will get to the thermodynamics of these reactions, as well as how we can explain this formation of ions at different levels of pH, and we would basically consider aqueous corrosion. Now, since I have mentioned aqueous corrosion, this corrosion can be divided into 2 parts. One is wet corrosion and another one is dry corrosion. Now, you must be wondering what is dry corrosion. If we recall that we have mentioned that oxidation is also a corrosion process. Now, whenever we talk about corrosion process, we have to see that whether this 4 parts of electrode, that particular cell, corrosion cell are being satisfied. Now, let us get to, as we have mentioned that corrosion can be wet and dry. Wet and dry corrosion. Now, in the wet corrosion, we see that where H2O is involved. We also call it aqueous corrosion. And in case of dry corrosion, we are mentioning that oxidation. Oxidation of metal, we are mentioning that this is also a corrosion. That means, it is also electrochemical. Aqueous corrosion, from those two examples, it is very clear, it involves oxygen, it involves water, because in one case we are dipping zinc metal into dilute HCl solution, which is aqueous solution of HCl, and in second case we are seeing that corrosion of iron object in the environment, in the atmosphere, where we have moisture, which is again water. Of course, there oxygen is also involved. But in case of dry corrosion, let us just have a look at what happens at the interface of metal when oxygen is involved, because anyhow I am talking about oxidation of metal. If we consider this particular reaction, O2 equal to half O2 MO, if I consider this oxidation reaction, let us have a look at what happens at the interface. This is metal surface. Let us say some oxide has formed MO, and then this is gas medium. Now, in the beginning there was, if we consider that there was nothing, so metal surface we are having M going to leaving 2 electron and then forming M plus 2. And if we consider oxygen, half oxygen, that means 1 oxygen atom, it takes care 2 electron and forming O2 minus. Since we are having this notation 2 plus and 2 minus, and if they combine, you see M plus half O2 equal to M plus 2 M2 minus two plus 2 minus. This is nothing but MO, which is same as this reaction. Now, interesting, let us look at carefully this. What is this reaction? This reaction is nothing but anodic reaction. Because the metal atom is leaving 2 electrons, it is basically oxidation is taking place, in the sense that if we consider oxidation to be electron, when metal leaves electron, we call it oxidation. Now, if I consider this reaction is nothing but a reduction reaction. Reduction or cathodic reaction, and this is oxidation reaction. Now, question is, 2 reactions are done. Now, since in the beginning we have only metal surface, we have oxygen and then metal. So, if this place we have metal plus 2 formation, so 2 electrons are released here in the metal. So, these 2 electrons are flowing through that conductor, and here half oxygen takes care 2 electron and forming O2 minus. This is 2 minus. So, these two are reacting. Now, you see this part acts as anode. So, one electrode, this part act as cathode, second electrode, this is conductor, and here when these two reactions are these hub cell reactions, these are called hub cell reactions. These hub cell reactions are taking place. Finally, metal 2 plus and oxygen 2 minus, they are combining and forming metal oxide. So, this metal oxide is forming on top of this metal surface. So, now we have situation like this. So, here metal surface, metal oxide and oxygen. Now, once we have this, now question is whether this reaction would continue or not. Now, still if I consider metal ion is forming, so 2 electrons are here and these electron can go somewhere around this metal object, because every metal part is basically acting as conductor. And now, this electron can flow through this, because metal oxide either it could be N type or P type. If it is N type, then this electron can flow through this, through the electron carrier, and then here can form 2 minus. Now, this ion can also move like this. Now, when it moves like this, it comes here and then combine with this and form metal oxide. Now, if metal ion is moving on the outer side and there this particular thing can combine and form metal oxide. Now, interestingly, charge flow is taking place through this. For example, here oxygen 2 minus is flowing, or here metal 2 minus is flowing through this. So, charge flow is taking through this MO. So, now MO becomes my electrolyte. And in case where oxygen ion goes through the metal oxide and reaches to the metal surface, and at the interface of metal and metal oxide, oxide forms, further oxide molecules are forming. That case the oxide growth is taking place on the metal oxide surface. So, on this surface oxide growth is taking place. Now, in case metal ion is moving out from the metal oxide interface and coming to the metal oxide oxygen interface, and there it combines with the oxygen ion, then the oxide growth is taking place on the surface of, or at the interface of metal oxide and gaseous oxygen. So, here also you are seeing that the condition of corrosion cell is satisfying. That means, we have cathode, we have anode, and in this case, since this cathodic reaction is taking place at this surface, at this interface, this becomes my cathode, and this particular reaction is taking place at metal oxide interface, this becomes my anode. And electron flow is taking place through the metal surface, or it can flow through the metal oxide. So, metal oxide itself is acting as electrode, acting as a conductor as well as electrolyte, because it also allows charge flow in the form of metal ion or oxygen ion. So, this is also electrochemical reactions, and here metal is oxidizing. So, metal is losing in the form of oxide, this is also corrosion. So, but here we do not have moisture. So, that means it is a dry corrosion. So, that is what we have come to the condition of dry corrosion where we have oxidation. If we have time, then we would definitely look into oxidation of metal little depth, but our primary interest would be on this aqueous corrosion. Primary interest. So, we will concentrate more on this in our present set of lectures. Now, before we go detail analysis, that means when I talk about analysis, we talk about thermodynamics and kinetics of this electrochemical reactions, either metal ion formation or cathodic reactions where electron is being accepted by some species. It can be iron, it can be metal, again another metal, or it can be another it can be oxygen. So, all those cases we would try to see their thermodynamics and kinetics. So, but for the time being we would again go back and try to see some of the forms of corrosion. So, next topic is forms of corrosion. For understanding these forms of corrosion, I think mere observation as well as a little bit of the idea of what we have already learned from this 2.5 lectures, you can say. That means that there would be electrochemical reaction, one is cathode, one is anode, one would be anodic reaction, one would be cathodic reactions. On that basis, we would be able to understand some of the forms. Forms means the kind of appearance, I would say. So, let us look at some of the appearances, okay? And then accordingly we define the forms of corrosion. Now, when we come to the forms of corrosion, if we have a kind of observation, rather careful observation, one form is uniform corrosion. Second form, galvanic corrosion. Third, crevice. Fourth, pitting. Fifth, de-alloying. We also call it in case of de-alloying or in case of iron brass, let us say, we call it de-zincification. Like that. Then we have intergranular, seventh, erosion corrosion, where we have two special forms. I would say two special forms. One is fretting, another one is cavitation, and finally we have stress assisted corrosion, where we have three segments. One is stress corrosion, then corrosion fatigue, and another one is hydrogen embrittlement. And in case of hydrogen embrittlement, we have few other forms. For example, hydrogen blistering is one form. And these particular definitions of different forms are basically arriving from the appearance. Like let us when for example, if we consider uniform corrosion, as we mean by uniform means it is homogeneous, uniformly happening. Like one example let me put up, if we see iron made sheet cover over a roof, one can find that after some time you will have a red rust formation over the entire surface, and if it is carefully looked at a little carefully looked at the interface, you would see that at different sections we would have almost about similar depth of attack. I would say depth of attack means the corrosion is gradually progressing towards the depth direction of the metal surface. So, at every sections we would have almost about similar depth of attack. So, that time we call it uniform corrosion. So, it is a form, it is basically appearance of that particular mode. Now, for example, pitting corrosion. When we talk about pitting corrosion, we know this particular name pitting. For example, on a surface, as if from the appearance you would see that there is no problem, because it is as shiny as it was obtained in the as received condition when it was obtained first. But the pitting can be extremely localized, and again if we carefully look at and analyze, we would see that at some positions the depth of attack is extremely localized and it has gone very far towards the depth direction of that metal surface, but rest of the surface looks absolutely fine. Similarly, crevice, this is also appearance. For example, let us say crevice means wherever we have a small opening in the metal structures or metal bodies, and in that small opening, that opening should be enough so that it can allow solution to go in, but the solution would remain stagnant into that particular metal opening. So, that case that would create a kind of corrosion, localized corrosion, rest of the surface would look shiny, but in that localized portion you will have red rust in case of iron, if I consider iron surface. Again appearance. Now, de-alloying, interestingly, if we have a brass 70-30, 70% copper and 30% zinc, and that brass if you dip it in HCl, dilute HCl solution, after some time we would see that the color, generally in the beginning the color of the brass is little golden yellow, and then when you expose it to into the acid, after some time you would see the surface is becoming a bit red colored. And if we analyze it, that for example, the analysis tool is for example ACM EDS, if we do, then we would see that the copper content has gone up from 70% to even close to around 92-93%. So, now at the surface that means copper is enriching, and if we look at that copper surface under the microscope, you would see that the copper surface is porous in nature. So, now here zinc, where is then zinc? Because in the beginning it was 30% zinc. So, now zinc content has gone down to 1 or 2% in that particular copper enriched region. So, the zinc has gone out into the solution and copper has been left out, and that forms a particular mode of corrosion which is called de-alloying. Since zinc is going out, that is what we call it de-zincification. So, like that. So, those are basically appearance. Now, if we try to analyze some of those all those variations, then we would also see some interesting part, that all those variations we will see that they are decided by some factors. Generally, if we see those factors, we will categorize into 5 major sections. One is materials, definitely material, and when I talk about material, that means if I consider these particular forms on a particular material, then material composition is fixed. So, that time we talk about microstructures. That time we talk about microstructure. since we are fixing the composition. Now, then we have environment. This environment is a very big thing, and in nutshell we can say that when we talk about aqueous corrosion, environment, the influence could be from oxygen, from moisture content, from SO2 content, or there could be possibility of presence of some metal ions. For example, Fe3 plus ion, if somewhere it is there, this Fe3 plus is not good, because Fe3 plus allows a greater corrosion to happen in case of, for example, we have given this example, zinc dipped in dilute HCl. If we have little bit of impurity FeCl3, that means Fe plus 3 ion is there, so the corrosion rate of zinc would be much higher than in the solution where FeCl3 is not there. So, those metal ions. Then of course, the other factors like temperature, those factors will come into picture. Then we have of course stress. Stress is important when we talk about stress assisted corrosion. One particular example we have put forth, that is silver bridge, crumbling of silver bridge, that people said that the reason behind that crumbling of silver bridge was stress corrosion and corrosion fatigue. Then we have, this is 1, this is 2, 3, then of course we have design. Design factor makes a huge impact. For example, if a smooth surface and rough surface, smooth surface of course it will have a less corrosion effect than the rough surface in general. Finally, fifth is the time. Of course, if something is exposed for longer duration, of course there will be corrosion would be more. So, these 5 major factors are crucial. So, in my next lecture I would talk about these 8 forms of corrosion in nutshell. We will not go greater depth into it, into this particular corrosion mode, because that is not our purpose. Our purpose is to understand the fundamentals of corrosion, and then of course on the way we will see that the effect of these 5 factors. Let us stop. We will continue in our next lecture. Thank you.